Hi again, everybody, and welcome to the continuation of example 2. In this problem, we'll be doing part B, which again, the exercise is asking us to take the graph that we're given of the function f and to do our best to sketch the graph of the derivative. Okay, so let's approach this the same way that we approach part A. We could start by asking, are there any places on the graph of f where the slope looks like it's 0? Okay, and as I look left to right, I really only see one point where it looks like our graph is pretty flat and horizontal, maybe right there. And so that means that because the slope is 0 at that point, the y value of our derivative has to be 0 there. Okay, so it gives us a starting point, one point that's on this derivative graph that we're going to draw. Okay, and now let's see if we can figure out what's going on either side of that point. So we can maybe look at this stretch of f. Okay, and what kind of tangent line slopes do we get on that stretch? Okay, if we start drawing in tangent lines, what do you see, positive or negative slopes? I'm seeing negative slopes, and that means because the slopes of the function are negative, that means the y values of the derivative have to be negative. Okay, so on that same stretch, it's going to have to be below the x-axis, maybe something like that. Okay, again, we don't know for sure how low it goes, but we do know that it's below the x-axis. Okay, and then next, we can maybe look at the part of the graph of f way over at the right here. And what about the tangent lines on that stretch? Are they positive or negative sloped? Okay, I'm seeing a bunch of negative slopes again, which means that the derivative graph is also below 0 on that side. Okay, so, whoops. Still getting used to this iPad a little bit. Okay, oh boy. Okay, so maybe something like that. Okay, so far that's what our derivative graph looks like. Okay, and now we come to the more interesting parts of this. So let's take a look at this stretch of our graph f. Okay, first of all, what kind of a slope do you see along that stretch, positive or negative? Okay, I see a line of positive slope, which tells us that the derivative graph is going to have to be above 0 on that stretch. But there's another interesting feature to this part of the graph. Does the slope ever change on that stretch? It doesn't, because it's linear, so every tangent line that we draw has the same slope. And so what that means is that since the slope is not changing, I'm going to actually write that in words, the slope is constant on that stretch of the graph. That means that the y values of our derivative should be constant. So we want to draw our derivative graph so that the y values are positive and they don't change. How do we do that? Okay, well, a graph that's positive and constant just looks like a horizontal line. Okay, so maybe something, oops, there I go again, not being able to draw a straight line. So something like this, maybe. Okay, and then the last point here, let's clear away a little bit of clutter. There's something kind of special going on at this point right here. This is what's known as a cusp. Okay, that's a word for a sharp corner on a graph. We get sort of a sudden change in slope there. And my question to you is, do we have a tangent line? Can we draw a tangent line at that point? Well, if you think about it, because of the sudden transition in slope, there kind of isn't a unique way to draw a tangent line. I mean, we could draw it like this, or we could draw it like that, or we could draw it like that. So there's not just one slope at that point, one slope that we can think about. And so since we can't nail it down to just one slope, the derivative ends up being undefined at that point. There is no one slope to the function at that corner. And so we need to kind of put that in our derivative graph somehow, and the way of saying that there's no output value is just to put an open circle. Okay? And so that open circle just indicates that the derivative of f is undefined at this point. Okay, so anytime you have a graph where that happens, where you have a sharp corner, a sudden transition in slope, you're going to get this behavior, and your derivative graph is just going to have a hole in it at that point. Okay, and so there's our best approximation of the derivative. Notice kind of a strange looking derivative. It occurs in two pieces this time.